Okay, let's kick things off. So think about all the gadgets we use every day. Your phone vibrating,
Yeah.
the sensors in your car.
Uh-huh.
Often there's a tiny component inside, a piezoelectric material, doing some clever work, turning movement into electricity or, the other way around.
It's pretty fundamental stuff, really.
But here's the catch, right? The most common one, PZT. It contains lead.
Yeah, and lead, as we all know, is, well, it's not great for the environment or our health. It's toxic.
Exactly. So today we're doing a deep dive into this really fascinating search for lead-free alternatives.
Yeah.
Materials that can power our tech and be kinder to the planet.
And it's interesting because it feels like a niche area, material science, but
Yeah.
it's tackling a huge issue. PZT works really well performance-wise. That's why it's everywhere.
Right.
But this review we're looking at really hammers home the toxicity problem, the way lead can build up. It's a serious concern.
So the big challenge is finding something just as good, performance-wise, but without the lead.
Precisely. That's the core mission driving all this research.
And that's what this deep dive is all about. We've got this comprehensive review paper as our guide, looking at the latest developments, the applications popping up, and some really ingenious methods scientists are using.
And what's particularly interesting, I think, is how much they're relying on computer models now.
Yeah, the review mentions that using models to understand and actually improve these materials for greener tech.
If you step back, you see piezoelectric tech everywhere. Energy harvesting, medical devices, sensors, it's kind of foundational.
Definitely.
So swapping out lead for something eco-friendly would be a massive win. The review introduces the main families being looked at: BNT, BT, KNN, BLSF, lithium-based ones too.
Okay, so those are the contenders. But the review is pretty clear that right now they generally have a low piezoelectric response compared to PZT. That's the main roadblock, isn't it?
That is the central problem, yeah. Getting that performance level up.
So how are they doing that? How do you boost these lead-free materials?
Well, the review highlights a couple of key strategies that seem really promising. One is called phase boundary engineering, or PBE.
Phase boundary engineering.
Okay. And the other is coming up with creative multi-scale designs of piezoelectric composites.
Multi-scale composites. Sounds complex.
It is, sort of. It means working at different scales, from the atomic level up, mixing materials cleverly to get better results, playing with the structure.
Right. The review gets into lattice dynamics and phonon modes. It's a very fundamental down at the atomic level. It mentions perovskite structures specifically. Why is understanding that so critical?
It's actually fascinating. It boils down to how the atoms inside the material vibrate. Those are the phonon modes. How they vibrate is directly linked to how well the material converts energy, mechanical to electrical or vice versa.
Okay.
And researchers are using things like first principles, sensitivity analysis, digging into huge databases like the Materials Project.
The Materials Project database, yeah.
To really figure out this connection. They're finding that these atomic vibrations, the phonon modes, can actually be more important for piezoelectric behavior than other things, like internal strain or how easily it polarizes.
So the review talks about multiple stable optical phonon modes being like a fingerprint for how tolerant a material is to disorder. That's a neat analogy. What does that mean practically, this multiple phonon mode criterion?
Yeah, it's a good way to think about it. Basically, if a material has several stable ways its atoms can vibrate when you stress it or apply a field, it's less likely to be messed up by tiny imperfections or disorder in its structure.
Which can dampen the effect you want.
Exactly. Disorder often weakens the piezoelectric response. So this criterion helps scientists pick out new materials that have this kind of built-in vibrational stability. They should be more robust, perform better.
And they found materials this way.
They did. The review mentions ackermanite, Cyper2XK2 Pisti, PCC100A2LC207. By tuning the composition, guided by this idea, they got nearly a 20% boost in response. That's significant.
Wow, okay. So that's one approach. The review then jumps into specific materials. Let's talk about these KNCN ceramics, adding calcium, annealing, and nitrogen. Right. What does that do?
Right. So with KNCN ceramics, adding calcium is a clever trick to create what's called an RO phase boundary.
RO, rhombohedral orthorhombic.
You got it. It's like finding a sweet spot between two crystal structures. This specific boundary seems to optimize the key properties. D33, the piezoelectric strength, and QM, which is about mechanical efficiency, how well it vibrates without losing energy.
And the nitrogen annealing.
That step further refines the structure, cleans things up, and they found it gave a pretty nice 30% bump in both D33 and QM for one specific composition, 2K-NCN.
Okay, interesting. Next up, BNT, bismuth sodium titanate. It's got robust ferroelectric properties, the review says. But what are the catches?
BNT's got potential, definitely. High remnant polarization, meaning it holds its electric charge well, but a major challenge has always been pulling it, aligning those electric dipoles initially. It has a strong coercive field, meaning it resists that alignment.
So it's tough to get it set up right.
A bit tricky, yeah. And how you heat it and solidify it, the sintering process, really matters for its performance, the electromechanical coupling. Plus, you need high temperatures, over 1200 degrees C.
That sounds energy intensive.
It is, and you risk boiling off some of the bismuth above 1130 degrees C, which hurts performance.
So what are they doing to get around that?
Researchers are trying modifications. Adding a bit of KNN and gadolinium oxide, for instance, or incorporating other materials like PMN and BST into the BNT matrix. These tweaks can improve high-temperature performance, pushing the stable operating range up towards 150 degrees C, which is much more practical for many applications.
That thermal stability sounds critical. How else are they boosting that for BNT materials?
Well, there's another neat example with a related material, BNT6BT. They found that adding just a small amount of silver ag significantly raises the depolarization temperature, TNA.
That's the temperature where it loses its piezoelectric properties.
Exactly. They push it up by 45 degrees C without sacrificing the piezoelectric response itself. That kind of stability is huge for reliability.
Makes sense.
And the review also mentions using BNT single crystal films in simulations for PMUTs, tiny ultrasound transducers, potentially for high-res medical imaging.
Yeah.
Tweaking the crystal orientation there improves sensitivity.
Fascinating. Okay, moving on to BFBT ceramics by FO3-BTIO3, adding KHA3 or neodymium. What are the benefits there?
Right, BFBT. Adding KA-FO3CH, for short, helps get rid of these undesirable core shell structures that can sometimes form, leading to a more uniform material. And this boosts several key properties: polarization, how much it deforms under an electric field. Even just 1% CH makes a difference.
And the neodymium.
Separately, adding neodymium ND and using a specific polling method allowed researchers to achieve a really excellent piezoelectric constant, D33, of 325 PCN. That's getting closer to lead-based levels, especially since BFBT already has a high Curie temperature, meaning good heat tolerance.
And then there's lithium doping. That seems to pop up quite a bit. What's the magic of adding lithium?
Lithium is proving to be a really versatile tool. It can do several things according to the review. It can raise the Curie temperature, tweak other transition temperatures, and even lower the sintering temperature needed.
Oh, so it helps with manufacturing too.
Yeah, potentially saving energy. And specifically in KNN-based materials, lithium doping can help create that desirable mix of orthorhombic and tetragonal phases right at room temperature, which often correlates with much better piezoelectric properties.
Any numbers on that?
Yeah, they mentioned significant jumps in D33 up to 530 PCN in one lithium-doped BCTZ material and up to 181 PCN in KNLN ceramics with lithium. So small additions, big impact.
It's amazing how these subtle chemical tweaks work. Now, before we move to applications, the review really emphasizes computational tools, like the Materials Project. How is this database changing the game?
It's a huge accelerator. The Materials Project is this massive repository of calculated material properties. So instead of making and testing thousands of compounds in the lab, which takes forever and costs a lot,
Right.
researchers can computationally screen materials first, look for promising predicted properties. The review notes there's a ton of unsynthesized lead-free compounds in the database with potential. It helps focus the experimental work where it's most likely to pay off.
So it really speeds up discovery. Okay, great progress on the materials themselves.
Yeah.
But where are we actually using these lead-free piezoelectrics? Or where could we use them soon?
Oh, the applications list is definitely growing. The review gives lots of examples. Things like tiny nanogenerators using barium titanate BT or barium calcium BC, compounds to harvest energy from vibrations.
Like for powering small sensors.
Exactly. Or even wearable nanogenerators using zinc oxide, ZNO, on flexible polymers. Then there's medical ultrasound KNN-based ceramics are being developed for high-frequency imaging, offering good resolution and bandwidth.
And you mentioned actuators before.
Yeah, BNT-based ceramics, especially modified ones, are showing enhanced strain. They deform more, which is great for actuator applications. They're also making flexible sensors using composites of BNTST and PVDF polymer fibers.
So sensing, actuation, energy harvesting. What else?
Well, the general properties of KNN, BNT, and BT materials, good electromechanical coupling, suitable acoustic and dielectric properties make them attractive for a whole range of medical sensing jobs, both high and low frequency. One BNT-BT composite mentioned has a really high coupling factor.
And you mentioned VR earlier, feeling heat and cold.
Right. That was the thermohaptic device
Hmm.
example. Using bismuth telluride pellets, which are thermoelectric, not strictly piezoelectric, but related in terms of smart materials encased in an elastomer for wearable VR, feeling temperature changes.
That's seriously cool.
It is. And more on energy harvesting. Nanocomposites using Ba3 nanoparticles in polymer matrices are generating usable voltages. Some flexible generators made with specially aggregated Ba3 are pushing out up to 75 volts. And researchers have even hit D33 values over 1100 PCN in doped Ba3 ceramics, which is really impressive.
That's huge. Okay, the review also gets into something called photostriction and piezophototronics, combining light and piezoelectricity.
Yeah, this is a really neat area. Photostriction is basically when a material changes shape in response to light. It combines the photovoltaic effect light creating voltage with the converse piezoelectric effect voltage causing deformation.
Okay, so light makes it change shape directly.
Pretty much. Some halide perovskites do this well, but they often contain lead. So again, the search is on for lead-free options.
What are they finding?
Things like composites of photovoltaic polymers mixed with piezoelectric fibers. Also, inorganic materials like barium titanate, BaTiO3, single crystals, show measurable shape changes under laser light. And modified KNN systems are also showing good photo-induced strain, though sometimes the response time is a bit longer.
Are there any standout lead-free photostrictive materials?
The review highlights some modified BNT solid solutions that show really impressive photo-induced strain over 0.1% in one case, plus good efficiency and, crucially, fast response times, like under 10 seconds. Another modified BNT ceramic showed 0.08% strain under laser light, much faster than typical organic polymers. This could be useful for light-controlled actuators or sensors.
Wow, okay. So much potential. Now, the review spends a good chunk of time on the theory and modeling side. Why is computational work becoming so central here?
It really comes down to efficiency. Experiments are essential, of course, but they can be slow and expensive. You can only synthesize and test so many materials. Models let you explore possibilities much faster, test hypotheses computationally, and gain deeper understanding.
It's like a virtual lab bench.
Exactly. You can simulate different conditions, tweak compositions, predict behavior. It guides the experimental work. The review mentions various models, electromechanical, ones that include thermal effects, even magnetic effects, phase field models. They capture different aspects of the physics.
It mentions finite element analysis, FEA.
Yeah, FEA is a powerful computational workhorse. It's used to solve the complex equations describing how these materials deform and polarize under stress and electric fields.
And something called the Landau-Ginzburg-Devonshire free energy function. Sounds intense.
It's a core theoretical tool. It helps describe the energy landscape of these ferroelectric materials and how they transition between different phases like cubic, tetragonal, etc. as temperature changes. Understanding these phase transitions is key because the piezoelectric properties are often strongest near them.
So it helps predict how temperature affects performance.
Precisely. And then there's the phase field method. What's the advantage there? Phase field models are great for simulating the microstructure, how the tiny polarized regions, the domains, form and evolve. The pattern of these domains drastically affects the material's overall response. So simulating domain wall movement helps understand, for example, why polling works or how the material might age. Some researchers are doing incredibly high-resolution simulations with this.
And finally, building on the materials project idea, there's machine learning. How is AI helping here?
It's taking data-driven discovery to the next level. Machine learning models can be trained on existing data, experimental or computational, to find complex relationships between a material's composition, structure, and its properties.
So it can predict performance.
Yes, predict things like piezoelectric coefficients, thermal stability, maybe even mechanical durability. It can help identify the best dopants or compositions to try, sometimes suggesting combinations researchers might not have thought of. It's really accelerating the design cycle for new materials.
Okay, wow. So bringing this all together, It's clear there's been huge progress in developing these lead-free piezoelectric materials. They're becoming real, sustainable alternatives to the lead-based ones.
Definitely. We've seen the different material families, the clever tricks like phase boundary engineering and doping used to boost their performance.
Right, and the applications are expanding rapidly. Energy harvesting, medical imaging, sensors, actuators, even VR.
And underpinning it all is this growing power of computational modeling and machine learning guiding the way.
It really feels like we're on the cusp of something significant here.
I think so. And what's really exciting isn't just replacing lead, which is vital, but the potential for these materials, maybe combined with other effects like photostriction, to enable completely new technologies we haven't even conceived of yet.
That's a fantastic point. It's not just about substitution, but innovation. Well, this deep dive has definitely shown the pace of change in this field. As always, we've only scratched the surface, and the research papers referenced in the review offer much more detail for anyone wanting to dig deeper. It really gets you thinking about how these tiny materials could fundamentally change our electronics and build a more sustainable future.